You're not seeing this world in the present, but through particles of light that left everything around you before they ever reached your eyes. Every time you look at a star, you're not seeing it as it is right now. You're receiving an old message sent from a distant past, and among all those silent messengers, nothing is stranger than a photon, a particle of light that never stands still. Welcome to Drift into Quiet Knowing. Tonight, we will follow the path of a photon, not as a rushed flight through space, but as a deep journey into the nature of the universe itself. A photon may begin as energy in the heart of a star, pass through layers of hot, glowing matter, escape from a blazing surface, and then cross the darkness for minutes, years, millions of years, or even billions of years, before falling into a human eye, touching the mirror of a telescope, or leaving one tiny trace on a scientific sensor. A photon has no rest mass. In a vacuum, it travels at the speed of light. We cannot sit on a photon and see the world from its point of view, because according to modern physics, there is no valid frame of reference in which a photon is at rest. But we can follow its trail through science, through mathematics, through telescopes, and through the quiet imagination of the human mind. When you understand the path of a photon, you begin to understand why light is the way the universe remembers itself. You understand why looking up at the sky means looking backward in time, why a ray of sunlight on your hand may have begun in a natural nuclear reactor deep inside the sun, and why a faint point of light from a distant galaxy can carry a story older than all of human history. So let your body relax, allow your breathing to slow, and, if you would like, let your eyes rest. Tonight we will not chase light through speed. We will follow it through stillness, from the place where a photon is born, across the deepest reaches of space, until it becomes part of your awareness, your memory, and your peaceful sleep. First, let us begin with something that seems familiar, but is also very easy to misunderstand. A photon is not a tiny glowing marble flying through the dark. If we imagine it as a little speck of yellow dust, with a clear shape, a surface, and its own private clock, that image may be beautiful for the imagination, but it is not quite right according to modern physics. A photon is the quantum of electromagnetic radiation. To put it more gently, whenever light exchanges energy with matter, that energy is not handed over like a perfectly continuous stream of water. It is exchanged in separate little packets. One such packet is called a photon, and from this seemingly tiny idea, an entire doorway into quantum physics opened. When you see light from a lamp, a ray of sunlight on a curtain, a streak of moonlight on the surface of water, or a very distant star glittering against the night sky, you are not only seeing light in the poetic sense, you're receiving countless photons that have travelled through space, interacted with matter, and finally entered your eyes. Each one of those photons carries a certain amount of energy. That amount of energy is not random. It depends on the frequency of the radiation. The higher the frequency, the greater the energy of the photon. So a gamma-ray photon carries more energy than a violet light photon. A violet light photon carries more energy than a red light photon. And a red light photon carries more energy than an infrared photon with a lower frequency. The world of photons is not separated by colour in the emotional way humans experience it, but by frequency, wavelength, and energy. Imagine the electromagnetic spectrum as a very long instrument played by the universe. At one end are the deep, low, wide notes of radio waves, with very long wavelengths and very little energy in each photon. Moving upward, we meet microwaves, infrared, visible light, ultraviolet, X-rays, and then gamma rays at the highest end, where each photon carries a very large amount of energy. The human eye can only hear, so to speak, one very short range on that cosmic instrument. That small range is visible light, but the universe does not play only in the range our eyes can see. It speaks in radio waves from cold clouds of gas. It whispers through ancient microwaves left over from when the universe was young. It radiates warmth in infrared from stardust and planets. It reveals violently hot regions through X-rays, and in the most intense events, it emits gamma rays, high-energy photons that can come from exploding stars, jets of matter near black holes, or extreme nuclear processes. The important thing is that all of these forms belong to the same family. Radio waves and gamma rays are not two different substances. They are both electromagnetic radiation. Both can be described by photons, and they differ only in energy and wavelength. A red photon from a sunset and an X-ray photon in a laboratory are not two completely separate species. They are the same kind of messenger from the electromagnetic field, carrying different levels of energy. Just as a person can speak in a very low voice or a very high voice, photons can appear at many different pitches in nature. And from that pitch, scientists can infer the source, temperature, environment, and history of that light. Here, we need to slow down a little, because this is where the imagination can easily wander too far. When we say a photon is a particle, we should not think of it as being like a very tiny pebble. When we say a photon is a wave, we should not think of it as being like an ordinary ripple on the surface of a pond either. In quantum physics, a photon has properties that everyday language cannot fully capture. In some experiments, it shows discrete behavior, like individual quanta being recorded one by a detector. In other experiments, it creates interference, like a wave that can pass through many possibilities before it is measured. So the question, is a photon really a particle or a wave, is no longer precise enough. A better way to say it is this: a photon is a quantum object of the electromagnetic field, and when we measure it under different conditions, it reveals different sides of reality. This truth does not make the story less beautiful. On the contrary, it makes the path of a photon even deeper. A photon does not need to have the shape of a speck of dust in order to be real. It is real because it can transfer energy, carry momentum, be absorbed, be emitted, knock an electron away from a metal surface in the photoelectric effect, activate a molecule in your retina, and leave a trace on the sensor of a telescope. It does not need to resemble the familiar objects of everyday life. It belongs to another level of description, where light and matter meet through laws more subtle than our intuition. One of the strangest things about a photon is that it has no rest mass. We need to say this carefully. Having no rest mass does not mean having no energy. A photon has energy. It also has momentum. Light can create pressure. It can push on matter very gently, and under certain conditions, radiation pressure plays an important role in the lives of stars, in cosmic dust, and even in the idea of light sails used for traveling through space. But a photon has no rest mass, which means there is no state in which a photon stands still the way a stone can rest on a table. It has no resting version that we could weigh in the way we weigh an object with mass. In a vacuum, a photon always travels at the speed of light. That value is about 186,282 miles per second, which is exactly 299,792,458 meters per second. This is not just a fast number, it is a fundamental structure of modern physics. According to special relativity, the speed of light in a vacuum is the same for every inertial frame of reference, no matter how the light source is moving. If a lamp is sitting still and emits light, that light travels at the speed of light. If the light source is moving extremely fast, light in a vacuum is still measured at that same speed by inertial observers. This is one of the ideas that forced human beings to change the way they understand space and time. And because a photon travels at the speed of light in a vacuum, we cannot assign it a valid frame of reference in which it is standing still. This is where many popular explanations oversimplify things by saying, for a photon, time stops. That sentence sounds beautiful, but speaking like a physicist, we need to be more careful. We cannot truly say, for a photon, in the sense of a person sitting on a photon and looking at the universe, because a photon has no rest frame. Such a frame of reference does not exist in relativity. We can say that the path of light through space-time is a light-like path, or a null path, and that the space-time interval along that path is zero in mathematical language. But we should not turn that into a psychological story about how a photon experiences the world. A photon has no experience. It has no clock. It does not age like a living creature. It is a quantum of light described by the laws of physics. This careful wording does not make photons any less wondrous. In fact, it makes them more wondrous because it forces us to leave behind images that are too simple. We do not need to imagine a photon as a tiny conscious traveller. Instead, think of it as a connection between two events, the event in which it is emitted and the event in which it is absorbed. Between those 2 points, In a physical description, the photon carries energy, momentum, frequency, direction of travel, and information about the process that created it. If it is born from an atom, its frequency may reveal the energy difference between two electron states. If it leaves the surface of a star, its spectrum may tell us about the temperature, chemical composition, and motion of the layer of gas from which it escaped. If it passes through a cloud of gas between the stars, some of the light may be absorbed at special wavelengths, leaving dark lines in the spectrum, like fingerprints of the elements. So a photon is a messenger, but it is a messenger that does not write with letters. It writes with frequency. It writes with spectra. It writes with direction and polarization. It writes by having its wavelength stretched as the universe expands, or by having its path bent when it passes near an object with strong gravity. When an astronomer observes light from a star, they are not only taking a beautiful picture, they are reading photons like letters from a faraway place. Each photon that reaches a telescope is one tiny fragment of the story, and when billions of those fragments are gathered together, they can reveal a star's age, speed, composition, and even the presence of planets orbiting it. Let us take a very close example. When sunlight falls on a leaf, some photons are absorbed by pigment molecules in the leaf, especially chlorophyll. That energy can take part in the chain of processes called photosynthesis, helping the plant turn light energy into chemical energy. Other photons are not absorbed, but reflected or scattered, and then they enter our eyes. That is the part of the light that makes us see the leaf as green. So the same flow of photons from the sun can divide into many different fates. Some help nourish life, some become color in human perception, some turn into heat, and some continue scattering through the air. All of those fates serve the same truth. Photons are the way energy and information move from one place to another. When a photon enters your eye, it does not carry a complete picture. It is only a tiny quantum. But many photons together, arriving from many different points in the scene, with many different wavelengths and intensities, create the data your visual system uses to build an image. A photon can touch a light-sensitive molecule in a retinal cell and cause that molecule to change its shape. This very small change begins a chain of biochemical and electrical nerve signals. In the end, the brain builds the feeling of light, color, shape, depth, and motion. The world you see does not enter the mind as whole, intact objects. It enters through messengers of light. Each tiny photon helps turn the matter outside you into experience within you. That is why the path of a photon does not belong only to astronomy. It passes through biology, chemistry, technology, and the philosophy of perception. In a camera, photons are recorded by a sensor and turned into electrical signals. In solar panels, photons can transfer energy to electrons and create electric current. In optical fibers, pulses of light are guided along to carry information across very long distances. In medicine, X-rays help us see through internal structures of the body, because X-ray photons interact with soft tissue and bone in different ways. In radio astronomy, long-wavelength photons allow us to see cold regions of gas that the naked eye could never see. Human beings have learned not only to see light, but also to capture it, measure it, split it apart, guide it, amplify it, and decode it. But to understand what a photon truly is, we need to return to its energy. The energy of a photon is determined by its frequency through Planck's formula. Energy equals Planck's constant multiplied by frequency. This is not a dry detail. It is one of the shortest and deepest sentences in physics. It says that color, or more precisely frequency, is not merely the appearance of light. It determines the energy of each photon. A very intense beam of red light may contain a huge number of red photons, so the total energy of the beam is large. But each individual red photon still has less energy than each individual blue or violet photon. Intensity tells us how many photons there are, while frequency tells us how much energy each photon carries. Understanding this distinction is an important step toward understanding light like a scientist. The photoelectric effect is a classic example. If light is shone onto a metal surface, electrons can be knocked out. But what surprised physicists in history was that increasing the intensity of the light was not always enough to knock electrons out if the frequency of the light was too low. There could be many low-energy photons, but if each photon did not have enough energy to cross the required threshold, the electrons still would not be released in the way the photoelectric effect requires. On the other hand, light with a high enough frequency can knock electrons out even when the intensity is not high. This helps strengthen the idea that light exchanges energy in individual quanta. In that interaction, a photon transfers its energy to an electron in a way that cannot be fully explained if light is treated only as a classical continuous wave. This brings us to a beautiful image. A photon is like a coin of energy in nature, but that coin does not always have the same value. Its value depends on frequency. Radio waves have very small coins, gamma rays have very large coins. When matter receives a photon, it is not receiving some vague flow of energy, but specific packets of energy in specific interactions. In an atom, electrons can only exist in certain energy states. When an electron moves from a higher state down to a lower state, the difference in energy can be emitted as a photon. So atoms do not emit every color randomly. They emit photons with energies that correspond to their inner quantum structure. That is why spectroscopy became one of the most powerful tools in science. If you look at a flame with the naked eye, you see yellow, orange, blue, and red. But if that light is separated through a spectrum, we can recognize signs of the elements and molecules that are glowing. If you look at light from a star, you cannot touch that star, take a gas sample from it, or fly close to it. But the photon has done part of the work for you. It left the star carrying information about the atoms in the star's atmosphere, its temperature, pressure, magnetic field, and motion. When it reaches a telescope, it becomes data. When the data is analysed, the photon becomes understanding. A tiny particle of light, if read in the right way, can tell us what a faraway world is made of. And this is what makes the photon a central character in astronomy. Almost everything we know about the distant universe comes from light, or more broadly, from electromagnetic radiation. Human beings cannot travel to most stars. We cannot touch the Andromeda galaxy with our hands. We cannot place a thermometer in the atmosphere of a planet outside the solar system. But photons can travel from there to here. When they arrive, they do not speak in words, but they carry enough traces for us to reason from them. An absorption line in a spectrum can tell us there is hydrogen. A redshift can tell us that a galaxy is moving away. A tiny variation in starlight can reveal a planet passing in front of its star. Very weak polarization can suggest a magnetic field or the way light has been scattered. In this way, the photon is a bridge between what cannot be touched and what can be known. Still, we should also be humble. A photon does not always travel from its source to our eyes along a simple path like an arrow drawn on paper. In a nearly perfect vacuum, we can describe light as traveling in a straight line if there is no significant gravitational influence. But in matter, photons interact, are absorbed, are re-emitted, scatter, change direction, or turn their energy into another form. In an opaque object, light does not pass through easily because photons are absorbed and scattered many times. In transparent glass, light can pass through, but the speed at which the light signal travels through the material is lower than the speed of light in a vacuum because the electromagnetic field interacts with the charges inside the material. We need to be precise. The fundamental speed of light in a vacuum remains the basic limit, while light travelling more slowly through a medium is the result of interactions between light and matter, not because a photon has rest mass or becomes tired like an ordinary object. Every time a photon meets matter, its story can change direction. It can be absorbed by an electron and disappear as the original photon, transferring its energy into matter. It can be re-emitted in another direction. It can scatter almost elastically, keeping nearly the same energy while changing direction. It can take part in heating a dust grain, and then that energy can be emitted again as an infrared photon. So, the path of a photon is not necessarily a straight thread. It may be a chain of events in which light energy moves from one form to another, from a photon into matter, and then from matter into another photon. When we say a ray of light travels from one place to another, that is often a simplified way of speaking about countless tiny interactions underneath. Imagine a photon in sunlight reaching Earth's atmosphere. If it belongs to the visible range, it can pass through the atmosphere fairly well. But some shorter wavelength photons are scattered by gas molecules. This scattering is stronger for blue light than for red light, which is why the daytime sky looks blue. When the sun is low near the horizon, its light travels through a thicker layer of atmosphere. Much of the blue light is scattered away from the direct line of sight, leaving more red and orange light to reach our eyes. So a sunset is not only a beautiful scene, it is a gentle lesson about the path of photons through the atmosphere and about how tiny molecules in the air change the colour of the sky. At a deeper level, photons also remind us that the universe does not need to be loud in order to transmit information. A photon can travel through nearly empty space for many years without colliding with anything significant. It can leave a star before modern civilization exists on Earth, then arrive in someone's eye on a quiet night. During that journey, it carries no sound, no scent, no spoken story. But it carries frequency, energy, and direction. When it touches a measuring device, it allows us to connect the present with the past. What we call looking far away in astronomy is really receiving photons that left their source a very long time ago. The sky is not a screen showing the present. The sky is an archive of light letters arriving late. So before we go deeper into where photons are born and the long stages of their journeys through the universe, we need to hold one basic truth in mind. A photon is not only the light that makes things shine, it is the unit of energy transfer in the electromagnetic field during quantum interactions. It has no rest mass, no stationary frame of reference, travels through a vacuum at the speed of light, and has energy that depends on frequency. It can belong to the range visible to the human eye, but it can also be a radio wave, microwave, infrared, ultraviolet, X-ray or gamma ray. It can warm skin, feed plants, activate the retina, run technology, or tell us the history of distant galaxies. If we had to keep only one image, imagine a photon as a letter with no words, written in the laws of physics. The place where it is born is the sender. Its frequency is the voice. Its wavelength is the breath. Its direction is the address. Its interactions along the way are ink marks changed by the environment, and the place where it is absorbed is the moment the letter is opened. In the human eye, it becomes an image. In a telescope, it becomes data. In the mind of a scientist, it becomes a question. And when that question is pursued long enough, that tiny photon becomes knowledge about the universe. That is why the path of a photon deserves to be followed slowly. Not because the photon is slow, but because its meaning is so deep. From a quantum of light, we arrive at the nature of colour. From colour, we arrive at energy. From energy, we arrive at atoms. From atoms, we arrive at stars. From stars, we arrive at galaxies. And from galaxies, we realise that the universe had always been telling stories through light long before humans had language to name them. A photon does not say, "This is where I came from." But if we know how to listen through science, it will tell us. And tonight, as we continue following that trace, we will see that every ray of light, no matter how small, can be the opening of a story longer than a human life. Now that we understand a photon is not a tiny glowing marble, but a quantum of the electromagnetic field, we can move toward a question that is almost childlike, yet very deep. Where does a photon begin? In what moment is its first light born? And why, if they are all photons, do some fall gently on your hand like morning sunlight, while others carry so much energy that they can pass through matter, and still others have travelled across the universe almost since the beginning of time? One of the most common birthplaces of photons is inside the atom. Imagine an atom not as a simple little solar system, but as a quantum system with allowed energy states. An electron in an atom cannot have just any amount of energy at once. It can only exist in certain states. When an electron receives energy, it can move up to a higher state. When it returns to a lower state, the difference in energy can be released as a photon. That photon carries exactly the amount of energy the atom has lost. So the light emitted by an atom is not random. It is like a very delicate physical signature. Each element has its own energy levels, so its light has its own colours, spectral lines, and identifying marks. This is a beautiful idea. An atom does not need to write its name in letters. It writes its name in photons. Hydrogen has its own spectral lines. Sodium has its characteristic yellow glow. Mercury, neon, oxygen, hydrogen, helium, each one has its own way of emitting and absorbing light. When astronomers look at light from a distant star, they do not need to bring a spoonful of matter from that star back to a laboratory. They only need to split the light into a spectrum. In the very thin, bright and dark lines, photons tell them where they came from, which elements they encountered, and which layers of gas they passed through. A photon, when read in the right way, can become the testimony of matter at a distance no spacecraft can touch. If we burn a little salt in a flame and see a burst of yellow light, that is not only a display of colour. The sodium atoms have been excited, and when their electrons return to lower energy states, they emit photons with characteristic wavelengths. If we look at neon lights on a city street, that red-orange colour also comes from gas atoms excited by electricity. If we look at glowing tubes in a laboratory, each colour is one way an atom gives energy back to the world. A photon born here is like a quantum bell. When an atom is struck with energy, it rings in the notes it is allowed to play and then releases light. But not every photon is born from clear atomic transitions like that. Some photons are born from hot matter. When an object heats up, the charged particles inside it move more vigorously, interact more often, and the object emits thermal radiation. A metal bar that is not yet extremely hot may emit mostly infrared light, which our eyes cannot clearly see, but our skin can feel as warmth. When it becomes hotter, it starts to glow red. Hotter still, it may glow orange, yellow, and then white. The colour here does not appear because matter paints the light. It appears because the energy distribution of the emitted photons changes with temperature. The higher the temperature, the more high-energy photons the object emits. A glowing coal, the filament of an incandescent bulb, and the surface of a star are all telling the same story. Hot matter turns microscopic motion into light. In an ordinary flame, photons can be born from several different sources. Some of the light comes from molecules and atoms excited during chemical reactions. Part of the familiar yellow-orange glow of many flames comes from tiny soot particles heated until they shine. In the blue region of a clean gas flame, the light may be more closely related to temporary molecules formed during combustion. So even a quiet candle on a table is not simple. It is a small laboratory where chemistry, heat, and photons meet. Every tiny flash inside the flame is a sign of energy changing form, from chemical bonds into heat and then into light. If we move from a small flame to lightning, the birthplace of photons becomes much more violent. When the electric field in the atmosphere becomes strong enough, the air is ionized and a plasma channel forms. A huge electric current passes through that channel, heating the air extremely quickly. Molecules and atoms in the air are excited, ionized, and then emit light as they return to lower states or as electric charges recombine. The blinding light of lightning is not just a white streak across the sky. It is countless photons born in an electrical storm where nitrogen molecules, oxygen molecules, free electrons and plasma all take part in a moment of enormous energy. Thunder is the sound of air suddenly expanding. Lightning is the letter of light that reaches our eyes first, much faster than sound. And also from the air, but in a gentler and more distant way, come the photons born in the aurora. When charged particles from the solar wind are guided by Earth's magnetic field toward the regions near the two poles, they collide with atoms and molecules in the upper atmosphere. Oxygen and nitrogen are excited, and when they release energy, photons appear. The green, red, and pale purple light of the aurora is not magic separated from science. It is the spectrum of the atmosphere being gently struck by particles from the sun. An auroral photon is the child of space and atmosphere, of the solar wind and Earth's magnetic field. It is born very high above us, then falls into human eyes like a curtain of light breathing in the night. But if we want to find a great furnace where photons are born, we must go into the hearts of stars. There, the story is no longer about a single electron in an atom, and not about a chemical flame either. In the core of the Sun, enormous temperature and pressure cause hydrogen nuclei to take part in nuclear fusion, eventually forming helium and releasing energy. That energy appears in many forms within the hot, dense plasma, including high-energy photons and the kinetic energy of particles. But we need to be very precise. The visible sunlight falling on your hand today should not be understood as the exact same intact photon that was created in the core of the Sun and then flew straight outward. Inside the Sun, matter is far too dense. Photons and radiant energy are absorbed, re-emitted, scattered, and redirected countless times. What moves from the core to the surface is better understood as energy, diffusing through a maze of plasma, not a lonely particle of light flying straight like an arrow. Imagine the Sun's core as a blazing ocean, so dense that light has no straight path. A packet of energy is created by nuclear fusion, it does not leave in one free flight. The surrounding matter catches it, releases it, changes its form and redirects it. In everyday imagery, it is like a traveller in an endless forest, moving only a very short distance before being pushed another way, turning back, turning sideways, moving forward and falling back again. But at the physical level, we should not treat it as the same photon with a personal memory. Energy is the more enduring character in this story. Energy born in the core slowly moves outward through the radiative zone, then through the convective zone, where hot material moves in enormous currents and finally reaches near the photosphere, the visible surface of the sun. When light leaves the sun's photosphere, its journey becomes completely different. From there to Earth, it passes through space that is far emptier than the inside of the sun. The average distance from the sun to Earth means light takes a little over 8 minutes to reach us. More specifically, people often say about 8 minutes and 20 seconds, depending on Earth's position in its orbit. So when you see the sun, you see it as it was when that light left more than 8 minutes earlier. If some strange change happened on the surface of the sun right now, the light carrying that information would still need more than 8 minutes to reach Earth. No message carried by light can travel faster than light itself. A ray of sunlight on your hand is therefore a story with 2 layers. The first layer is very long, very tangled, and very hot. It belongs to energy created in the heart of the sun and gradually escaping to the surface through countless interactions. The second layer is much straighter and much faster. It belongs to a photon leaving the photosphere, crossing interplanetary space, and reaching Earth in a little over 8 minutes. When it touches your skin, some of its energy may become heat. When it touches your eye, some of it may become a visual signal. When it touches a leaf, some of it may take part in photosynthesis. From the core of a star to life itself, photons and light energy connect places that seem impossibly far apart into one continuous chain. This is what makes sunlight more moving when we understand it through science. Sunlight is not merely brightness, it is the result of gravity holding the sun hot and dense enough for nuclear fusion to happen. It is the result of plasma, the radiative zone, the convective zone, and the photosphere. It is energy that has crossed a gigantic maze, then passed through space to reach this planet. A photon does not know whether it will warm a roof, shine on the ocean, enter a child's eye, or be absorbed by an old leaf in the afternoon. It has no intention, but along that path without intention, it still becomes part of life. Other stars also give birth to photons in their own ways. A hot blue star emits more high-energy photons in the ultraviolet and blue light ranges. A cooler red star emits relatively more red light and infrared. When astronomers look at the colour of a star, they do not only see beauty, they see a sign of surface temperature. When they analyse its spectrum, they see the elements in the star's atmosphere. When they measure its brightness, distance, and changes over time, they infer its size, age, structure, and stage of evolution. Photons born at the surface of a star or escaping from the layers of gas around it become messengers of the entire physics of stars. Some photons are born in the death of stars. When a massive star ends its life in a supernova explosion, matter is thrown outward with enormous energy. In that explosion and in the remnant afterward, photons appear across many regions of the electromagnetic spectrum: visible light, ultraviolet, X-rays, gamma rays, and radio waves. Those photons do not only tell us that a star has died, they speak of heavy elements being created, of shock waves spreading through gas, of high-energy particles, and of the environment between the stars. The iron in blood, the calcium in bones, and the oxygen in the breath of living creatures are all connected to the history of generations of stars. And the light from those events is the way the universe leaves a record of the process that made complex matter. Even places that seem dark can give birth to photons. Human eyes simply cannot always see them. A cold dust cloud in space can emit infrared or submillimeter waves, meaning wavelengths below about 0.04 inches, or below 1 millimeter. A region of hydrogen gas can emit characteristic light when it is excited by nearby young stars. A disk of hot matter swirling around a compact object such as a neutron star or a black hole can emit X-rays. A black hole itself does not allow light from inside the event horizon to escape, but matter outside the black hole, as it is compressed, heated, and accelerated in an accretion disk, can become one of the strongest sources of high-energy photons in the universe. Here, Photons are not born from the darkness of the black hole itself, but from matter glowing in agony before part of it disappears beyond the region from which return is possible. In everyday life, we also meet much closer birthplaces of photons. An incandescent light bulb creates light by heating a filament to a high temperature, causing it to emit thermal radiation. A fluorescent lamp uses electricity to excite mercury vapor, creating ultraviolet light, and then a fluorescent coating turns that energy into visible light. Lights based on light-emitting semiconductor diodes create photons when electrons and holes recombine inside semiconductor material, releasing energy as light. Phone screens, computer screens, televisions, streetlights, and signs are all human-designed birthplaces for photons. Modern light technology is really the art of controlling the paths through which photons are born and absorbed. This makes the story feel close to us. Stars and galaxies are not the only things that give birth to photons. Your room is also full of photon sources. A light bulb on the ceiling, a glowing screen, a red coal in a fireplace, a reflection on a glass of water. All of them are taking part in the same natural language. Those photons have different origins, different energies, and different paths. But when they touch your eyes, the brain quietly gathers them into the familiar space around you. The table, the wall, your hand, the page of a book, everything appears through photons that are born, reflected, scattered, and absorbed. Still, the oldest birthplace we can observe is not inside a light bulb, not inside a flame, and not even inside the sun. It lies in the early universe. During the first few 100,000 years after the Big Bang, the universe was so hot and dense that free electrons constantly scattered photons. Light could not travel far along long, free paths. The universe then was like a bright but opaque plasma fog, where photons were constantly colliding with charged particles. Then, as the universe expanded and cooled, protons and electrons could combine into neutral atoms, mostly hydrogen and helium. When the number of free electrons dropped sharply, photons were no longer scattered constantly. The universe became transparent. Light from that moment began travelling freely through space. Today we observe that ancient light as the cosmic microwave background. It is no longer hot light in the way it was in the young universe. The expansion of space has stretched its wavelengths and cooled it into a very cold microwave background, almost uniform across the sky, with extremely tiny temperature fluctuations. Those photons are among the oldest messages we can receive. They do not come from one individual star. They come from the era when the entire observable universe was changing from opaque to transparent. If starlight is a letter from islands of fire in space, then the cosmic microwave background is like the faint echo of the first dawn when light was able to travel freely across long distances. Let us pause here for a moment. A photon from the sun takes a little over 8 minutes to travel from the photosphere to Earth. A photon from a nearby star can take many years. A photon from a distant galaxy can take millions or billions of years. But the photons of the cosmic microwave background that we measure today have traveled through most of the history of the universe, ever since matter and light separated enough for light to move freely. When a scientific instrument receives those photons, it is not only measuring a weak signal, it is touching a background layer of the universe's memory. No human eye can see it as a bright picture, but through antennas, satellites, and mathematics, human beings have turned those cold photons into a map of the young universe. From atoms in a laboratory to the cores of stars, from lightning to auroras, from a small screen to the cosmic microwave background, we see one unified truth. The place where a photon is born always leaves a trace inside the photon. A photon does not carry a passport, but it carries frequency. It does not carry memory like a human being, but it carries physical information. If it comes from hot matter, its energy distribution speaks of temperature. If it comes from an atomic transition, its wavelength speaks of the energy structure of the atom. If it has been stretched by the expansion of the universe, it speaks of the history of growing space. If it has been absorbed at one specific wavelength, it tells us that along its path, an element or molecule took exactly that portion of energy. And this is why the path of a photon is not a decorative story added onto science, but the backbone of how we understand the universe. Every photon begins somewhere, in some process. It may be born when an electron drops to a lower energy level, when hot matter emits radiation, when plasma is excited, when a charged particle accelerates, when a nuclear reaction causes energy to spread outward. or when the early universe becomes transparent, then it travels. It may be absorbed immediately, it may scatter many times, it may be transformed into heat, it may travel for billions of years, it may die inside a dust grain, it may live long enough to enter a telescope. But whatever its fate, the beginning of its story is always tied to the place where it was born. So a ray of sunlight falling on your hand is no longer ordinary. It is the intimate endpoint of a process that began in nuclear physics, passed through plasma, crossed space, moved through the atmosphere, and finally touched living matter. A streak of aurora in the sky is no longer only a beautiful sight. It is a sign of the sun, the magnetic field, and the atmosphere writing light together. A line in a spectrum is no longer a lifeless thin mark. It is the signature of an atom saying, "I was here." And a cold microwave background coming from every direction is no longer background noise. It is ancient light, arriving from the time when the universe first allowed photons to travel far. But the strangest thing is still this: a photon does not need to know where it is going. It has no purpose, no memory, and no desire to be seen. It only follows the deep laws of nature, and yet, when it touches a human eye, it can help a memory appear. When it touches the sensor of a telescope, it can help a distant galaxy enter human understanding. When it touches a leaf, it can help nourish a living being. When it leaves the early universe and reaches a modern detector, it can help us reconstruct the history of all the great structures we see today. There is no intention inside the photon, but there is meaning in the way we read it. The place where a photon is born decides the beginning of its story. A photon born in an atom carries the trace of energy levels. A photon born in hot matter carries the trace of temperature. A photon born in lightning carries the trace of atmospheric plasma. A photon born from an aurora carries the trace of oxygen, nitrogen, the solar wind, and the magnetic field. A photon leaving the sun carries the trace of the nearest star that has nourished this planet. An ancient photon from the cosmic microwave background carries the trace of the moment space became transparent. All of them, different as they are, serve the same message. The universe is not absolutely silent. It tells stories through light, and photons are the smallest syllables in that story. From the place where a photon is born, the next part of the story no longer belongs only to fire, atoms, the sun, or the early universe. It begins to open into something much greater. Once a photon has left its source, it becomes a messenger of space. It does not need wings. It does not need fuel. It does not need to rest along the way. In a vacuum, it travels at the speed of light. And because that speed is finite, the sky we see is never the sky of this exact moment. Every image arrives a little late. All light is the past touching the present. This sounds very strange, because in everyday life, light seems to arrive instantly. You turn on a lamp in a room, and the room lights up with almost no delay that human senses can notice. But that is only because the room is too small compared with the speed of light. On Earth, across the distance of a house, a street, or a field, light travels so quickly that we feel as if it takes no time at all. But in the universe, distance is no longer a few feet, or a few meters, nor a few miles, or a few kilometers. Distance becomes hundreds of thousands of miles, or hundreds of thousands of kilometers, millions of miles, or millions of kilometers, trillions of miles, or trillions of kilometers, then light years, millions of light years, and billions of light years. When space becomes that large, even light needs time to travel. Let us begin with the moon, the most familiar object in the night sky. When you look at the moon, you're not seeing it exactly as it is in this absolute moment. Reflected light from the moon takes a little more than 1 second to reach your eyes. Just a little over 1 second. Very short compared with a human life, but enough to remind us that seeing means receiving a message that has already set out. The moon you see is the moon of the very recent past. It is not far in the cosmic sense, but even that closeness already carries the delay of light. Then we look to the sun. Light from the visible surface of the sun needs about 8 minutes and 20 seconds to reach Earth. That means when you see the first morning sunlight pouring through a window, that light left the sun more than 8 minutes earlier. If we imagine this carefully, no information carried by light from the sun can arrive here faster than that limit. The sun in the sky is the sun delivered to us by light with a small but real delay. So every sunrise is not only the beginning of a day, it is a letter that has just arrived after a journey of about 93 million miles, or 150 million kilometers. Farther out, that delay is no longer counted in seconds or minutes. Light from the nearest stars must travel for years before it reaches our eyes. When we look at a star 4 light-years away, we are seeing light that left that star 4 years ago. Some stars in the night sky have light that travelled for decades, centuries, or even thousands of years before reaching us. There are points of light that our distant ancestors once saw with the naked eye, and today we still see them, but each time we look we receive different photons, leaving their sources at different times. The sky is like a choir of many eras in which each star is singing from its own distance. This completely changes the way we understand the sky. The night sky is not a flat picture hanging above us, it is an archive of time. Brighter, nearer stars bring newer letters. More distant star clusters send older letters. Faint galaxies, if captured by a telescope, may be sending light from a time when Earth was very different, or even from before many complex forms of life, like those we know today, existed. The deeper the space, the farther the past. Looking far away is not only looking toward another place. Looking far away is looking toward another time. A telescope, then, is not merely a magnifying tool. It is a machine for the archaeology of light. An archaeologist on Earth digs down through layers of soil to find traces of the past. An astronomer does not dig into the ground. They look deep into space. Each more distant layer of the universe is an older layer of time. A telescope collects photons that began their journey long ago, gathers them with mirrors or lenses, and turns them into data. A faint smudge in an astronomical image may be a galaxy containing billions of stars. But what makes it even more wondrous is this. We do not only see that galaxy far away, we see it when it was much younger than it is now. Imagine a photon leaving a distant galaxy. When it begins its journey, the solar system may not yet have the landscapes we know today. Earth may still be in a completely different biological stage. While that photon quietly crosses space, mountains rise and erode on this planet, oceans change, life evolves, extinctions happen, new species appear. Human beings learn how to make fire, paint cave walls, build cities, make glass, and finally construct telescopes sensitive enough to catch it. The photon knows nothing of that journey, but when it touches the sensor of an observatory, that entire long silence suddenly becomes one data point inside human intelligence. For very distant galaxies, light may have travelled for billions of years. This does not mean we are seeing a galaxy as it exists there today. We are seeing it as it once was, when the photon left it. A galaxy in a deep telescope image may have changed a great deal, merged with another galaxy, formed more stars, or aged in ways we cannot yet see. Its present information has not reached us. The universe does not let us see everything in one absolute moment. It gives us a picture built from different delays of light. There is a deep beauty here. The very limit of the speed of light is what gives human beings the ability to look backward in time. If light arrived instantly from everywhere, the sky would only be the present. But because light needs time, each photon becomes a piece of the past preserved in motion. It does not preserve the past through memory, but by still travelling. A photon leaving a distant galaxy does not tell a story in words. It simply exists as a quantum of light moving forward. But that existence is enough to hold on to an old moment of the universe until it is absorbed somewhere. When we say light year, we're using time to measure distance. 1 light year is the distance light travels in 1 year in a vacuum. The phrase sounds like a unit of time, but it is actually a unit of length. And this beautiful blending reminds us that in astronomy, space and time are always woven together. Saying a star is 10 light years away also means its light needs 10 years to reach us. Saying a galaxy is millions of light years away also means the image we receive left that galaxy millions of years ago. Distance becomes the age of light. From that point of view, every time we look at the night sky, we're not looking into one single now. The moon is a little more than 1 second ago. The sun is more than 8 minutes ago, if it is in the sky. The planets are a few minutes to a few hours ago, depending on where they are in their orbits. The stars are many years ago. Star clusters and nebulae may be thousands of years ago. The Andromeda Galaxy appears as light that began its journey about 2.5 million years ago. More distant galaxy clusters send us light from eras when Earth's history was completely different. All of them share the same sky, but not the same moment. The sky is a map not only of direction, but of time. And then we need to ask, how does a photon travel through space? In a simple image, we may draw it as a straight line. That is nearly correct in regions of space far enough from objects with strong gravity, and when we ignore the expansion of the universe on large scales. But general relativity gives us a deeper picture. Light does not move across a perfectly flat stage of space. It moves through space-time, and space-time is curved by matter and energy. In general relativity, a photon follows its natural path through that geometry. To us, that path may appear bent when light passes near a massive object such as a star, a galaxy cluster, or a black hole. This is gravitational lensing. A galaxy cluster with enormous mass can bend the path of light from a galaxy far behind it. As a result, the image of the background galaxy may be stretched into a bright arc, magnified, distorted, or appear as multiple images. A giant object in the universe can act like a lens, not because it is made of glass, but because its mass curves space-time. When light passes through that curved region, the photon's path changes. Because of this, nature sometimes gives us a gigantic telescope of its own, allowing us to see galaxies that are farther away and fainter than we normally could. This has great meaning. A photon does not only tell us where the light source is, the way it is bent also tells us how much mass lies along its path. Even dark matter, which does not emit light and does not absorb light the way ordinary matter does, still has gravity. It still helps curve the path of light. By observing the distorted shapes of distant galaxies, astronomers can map the distribution of mass, including the part that cannot be seen directly. At this point, the photon is not only a letter from a distant galaxy, it is also a geometric ruler for spacetime along the way. Imagine a photon leaving a young galaxy behind a massive galaxy cluster. It travels for billions of years, and then, when it comes near the cluster along the way, the spacetime around that cluster bends its path slightly. Other photons from the same background galaxy may take different routes around the cluster and still arrive at Earth. Because of this, we may see several images of the same galaxy, or a nearly circular ring called an Einstein ring if the alignment is special enough. To the naked eye, this would look as if the universe were looking into a mirror, but in science, it is evidence that light is travelling through the curved geometry of space-time. And if a light can be bent by a galaxy cluster, then near a black hole, the story becomes even deeper. A black hole is a region of space-time where gravity is so strong that inside the event horizon, light cannot escape outward. A photon outside a black hole can be strongly deflected if it passes close by. There are very special paths around a black hole, in which light can move along unstable circular orbits in a region called the photon sphere, for an ideal non-rotating black hole. But those orbits are not stable. Even the tiniest difference can cause a photon either to escape outward or fall into the black hole. Near a black hole, the path of a photon shows that the geometry of spacetime is no longer a gentle flat background, but an extreme curved abyss. We must be careful with this image. A black hole is not a machine that sucks in all light from infinitely far away. If a photon passes far enough away, it may only be slightly deflected, just as light is bent by any mass, only much more strongly when it comes close. But if a photon travels inside the event horizon in a direction from which it cannot escape, then for the outside universe, its return journey has ended. No photon from inside the event horizon can carry information outward. So a black hole is a place where the path of a photon becomes the boundary of what can be observed. Light can also change not only in direction, but in wavelength. When a photon climbs out of a region with strong gravity, it can be shifted toward the red because it loses energy in the way described by general relativity. When a photon travels through the expanding universe across very large distances, its wavelength is also stretched. This is cosmological redshift. A photon originally emitted in the ultraviolet or visible range from a very distant galaxy may reach us in the infrared, because during the photon's journey, the space between galaxies has expanded. Light is stretched along with the growth of the cosmic scale. Redshift is one of the important pieces of evidence that helps us understand that the universe is not standing still. When familiar spectral lines from elements in the light of galaxies are shifted toward longer wavelengths, Astronomers can measure that shift to infer information about distance and the history of expansion. This is not just the colour of light becoming redder in the ordinary visual sense. Often, the light has shifted outside the range the human eye can see. Infrared telescopes become important because they collect ancient light that has been stretched after a long journey through the universe. The longer a photon travels through the expanding universe, the more the story of its wavelength carries the trace of that expansion. So the path of a photon does not only tell us distance, it also tells us how the universe changed while the photon was travelling. A photon does not cross a motionless stage. It travels through a universe with structure, gravity, galaxy clusters, vast empty regions, and large-scale expansion. Along the way, it may be bent by mass, have its wavelength stretched by expansion, be absorbed by gas, be scattered by dust, or pass almost unchanged through immense emptiness. When it finally reaches us, it carries not only information about where it was born, but also traces of the journey itself. That is why a deep astronomical image is never just a beautiful picture. It is a record of many photon paths. Some photons come from stars in our own galaxy. Some come from nearby galaxies. Some come from galaxies much farther away, smaller in the image but older in observed time. Some photons have passed through the gravitational field of a galaxy cluster and been stretched into bright arcs. Some photons have been reddened by cosmic dust. Some began as higher energy light but were stretched in wavelength into infrared. All of them are placed into the same frame, like many pages of history stacked inside one map. And if we listen very slowly, there is something strangely comforting in this. The universe does not give us the past in a loud voice. It sends individual photons. A photon that arrives after millions of years does not complain about the distance. It simply arrives, is absorbed, and becomes a signal. That signal enters an instrument, becomes numbers, becomes an image, becomes inference, and then becomes understanding. From a very faint point of light, human beings can learn how actively a galaxy once formed stars, which elements its gas contained, how fast it is moving away, and how much its light has been stretched by the universe. A very small photon can open a very large door. Let us return to the human eye for a moment. When you look at a star in the night sky, the photon that finally touches your retina may have left that star before you were born. It may have left before your parents were born. It may have left before many historical events took place. It travelled through darkness and silence, not knowing that at the end of its path there would be a pair of eyes looking up. And when it is absorbed by a light-sensitive molecule in your eye, its physical journey ends, but another journey begins. A nerve signal, an image in the mind, a feeling of vastness, and the quiet question of where we are in this universe. In a telescope, the story is similar, but expanded by technology. A large telescope mirror does not only make objects look closer, it collects more photons. With very faint objects, the problem is not only magnification, but gathering enough light. A distant galaxy may send very few photons to every 10.8 square feet, or 1 square metre, of Earth every second. To see it, we need large mirrors, long exposure times, sensitive sensors, and refined ways of removing noise. When enough photons are collected, what seemed invisible begins to appear. A faint streak becomes a galaxy. A weak dot becomes a supernova. A tiny variation becomes the sign of a planet outside the solar system. Here, we see more clearly than ever. Photons are the bridge between what cannot be approached and what can be understood. No one needs to fly to a galaxy billions of light years away to know it exists. Photons have travelled for us. No one needs to touch a galaxy cluster to measure its mass. The bending of light has spoken for it. No one needs to stand in the early universe to know how hot and dense it was. Ancient photons, along with other traces, have given us a map of that era. In cosmic science, we do not possess the past. We only receive the messengers that can still reach us. But the path of a photon also teaches us about limits. Because light needs time, we cannot instantly know everything that is happening far away. The picture of the universe is always a picture of different moments. Some regions are so far away that light from them has never had enough time to reach us since the universe began. There are regions from which, because of the expansion of the universe, light emitted in the future may never reach us. The observable universe is not necessarily the entire universe if the whole universe is larger. It is the part of the universe from which photons and other signals have been able to bring information to us during the finite history of the universe. This does not make science smaller. It makes science more humble and more beautiful. We learn that all our understanding is built on what can reach us. Every photon received is a physical stroke of luck. It was not absorbed by dust. It did not fall into a black hole. It was not scattered away from its path. It crossed space, gravitational fields, and the expansion of the universe until it was finally recorded. A photon that reaches a telescope is a messenger completing its mission after a journey that human imagination can barely hold. So when we say the path of a photon turns space into history, that is not a poetic image separated from science. It is the essence of astronomical observation. The finite speed of light makes every distant observation an observation of the past. The curved geometry of space-time allows the path of light to be bent, magnified, and split into multiple images. The expansion of the universe stretches the wavelength of photons as they cross great distances. Matter between stars and between galaxies can absorb or scatter part of the light, leaving traces in the spectrum. All of this turns a photon into a record of both its source and its journey. The night sky, then, is no longer a distant emptiness. It is a library falling into our eyes one quantum at a time. Each star is a bright page from its own moment. Each galaxy is an old chapter of the universe. Each arc of gravitational lensing is a sentence bent by mass. Each redshift is a stretch mark of space. And each photon that reaches us is a piece of the past still alive. Not alive like a creature, but alive in the sense that it can still transmit information. When it is absorbed, that past is no longer light in flight. It becomes data, image, understanding, and sometimes a quiet feeling in the mind of the person looking up. If tonight you imagine a photon leaving a distant galaxy, give it a very slow journey in your mind. It leaves a bright star-forming region, passes through the thin gas of its home galaxy, and escapes into intergalactic space. It moves through regions almost empty, where the density of matter is so low that millions of years may pass with almost no significant collision. It passes near a galaxy cluster, and its path bends slightly. Its wavelength gradually stretches as the universe expands. Then finally, after a span of time longer than the history of mountains, seas, and familiar human life, it falls into the mirror of an observatory. There it is no longer a wanderer. It becomes part of the answer, and that answer always returns to the same message. The universe tells stories through light. Where a photon is born is the opening. The path it travels is the body of the story. The place where it is absorbed is the final period of a physical journey, but it can also be the starting point of knowledge. When we look up, we're not only looking at distant objects, we're receiving old moments, curved paths, stretched wavelengths, and delicate signs of matter and space-time. The path of a photon turns distance into memory, and within that memory, the sky becomes the gentlest time machine nature has ever given us. After travelling through space and carrying fragments of a very distant past, a photon eventually has to meet something. It may meet a speck of dust between the stars, a gas molecule in the atmosphere, a leaf in the garden, a window pane, a still surface of water, human skin, the retina inside an eye, the mirror of a telescope, or a thin sensor inside a camera. And it is in that moment of meeting that light is no longer only a path across the universe. It becomes colour, temperature, image, data, life, and finally, awareness. When a photon meets matter, nature opens many possibilities. It can be absorbed, meaning its energy is transferred into matter. It can be reflected, meaning the light leaves a surface in a new direction. It can pass through, as when light moves through glass or clear water. It can be scattered, meaning it changes direction in different ways as it interacts with small particles, molecules, or uneven structures. It can also move an electron in an atom or molecule into a higher energy state, or take part in deeper processes such as the photoelectric effect, photosynthesis, or the signals inside visual cells. All of these possibilities share the same meaning. Photons are the way the universe gives energy and information to matter. Let us begin with something very familiar: colour. An object does not contain colour in the way a box contains things inside it. A red flower does not store redness as an independent substance hidden in its petals. A green leaf does not keep green like paint in a can. Colour appears when light interacts with matter, and then the remaining light enters our eyes. If a surface strongly absorbs many wavelengths, but reflects the wavelengths that the eye and brain perceive as red, we call that surface red. If a leaf strongly absorbs blue and red light because of photosynthetic pigments, but reflects or transmits more light in the green range, we see the leaf as green. So colour does not exist only in the photon, and it doesn't exist only in the object. It appears in the relationship between the light source, matter, the eye, and the brain. A single photon does not have colour in the emotional human sense. It has energy, frequency, and wavelength. Colour is the way the visual system interprets photons in the visible light range. This is a very important point. When we say a red photon, we're using shorthand to say that the photon has a wavelength or frequency in the range that the human visual system usually experiences as red. The photon itself does not carry a little piece of red paint. It carries energy, and when that energy interacts with molecules in the retina and is then interpreted by the brain, the experience of red appears in awareness. This makes the everyday world more wondrous. You do not truly see a flower by touching it. You see photons that have left the flower, carrying information about its surface, pigments, shape, moisture, lighting direction, and surrounding environment. Those photons enter your eyes, are focused, are absorbed in the retina, and then become nerve signals. The flower out there does not enter the mind whole and intact, only light enters. And from that light, the brain builds the image of the flower. When a photon is absorbed, the journey of that individual photon ends. But its energy does not disappear. That energy may become heat, making molecules vibrate more strongly. It may lift an electron into a higher energy state. It may begin a chemical reaction. It may create an electrical signal in a semiconductor material. It may change the shape of a light-sensitive molecule in the eye. In other words, a photon can disappear from the path of light, but its story continues inside matter. It is no longer light in flight, but the energy and information it carried have been transferred into another form. Look at a leaf under sunlight. Some photons from the sun touch the leaf surface and are reflected, helping our eyes see the colour green. Some go deeper into the leaf tissue and meet pigment molecules inside chloroplasts. When a suitable photon is absorbed by a pigment, its energy can excite an electron inside that pigment molecule. In photosynthesis, light energy is passed through complex molecular systems, helping create chemical energy that the plant uses to build organic matter. From a very small point of view, a photon from the sun can begin a chain of transformations inside a leaf. From a very large point of view, starlight has become food, stems, shade, breath, and life. The same light can have many fates. A photon absorbed in photosynthesis may help nourish a plant. Another photon reflects off the leaf and enters your eye, becoming green in awareness. Another photon is absorbed by the ground and becomes heat. These are not three separate stories. They are three branches of the same truth. Photons connect the energy source of the sun with matter on Earth. They warm, illuminate, nourish, and allow us to see. A tiny quantum of light can belong at once to stellar physics, the biology of plants, and the quiet human experience of looking at a garden. Reflection is another way photons tell a story. When you look into a mirror, you are not seeing your own face through some mysterious miracle. You are seeing light from your face travel to the mirror, interact with electrons in a very thin metallic layer, and then reflect according to a clear geometric rule. The angle of incidence equals the angle of reflection. At a deeper level, reflection is not a tiny ball hitting a wall and bouncing back in a crude mechanical sense. It is the interaction of the electromagnetic field with electric charges inside the material. Those charges respond to the incoming light, and the electromagnetic field produced by that response creates the reflected light. The familiar geometry of a mirror is the large-scale result of countless microscopic interactions arranged with extraordinary precision. A calm lake can also reflect the sky, but not like a perfect mirror. Some light is reflected at the water surface, some passes into the water, and some is absorbed or scattered by suspended particles. That is why we may see both the image of the sky on the lake surface and the dim depth below it. A window pane behaves in a similar way. It transmits much visible light but still reflects some of it. During the day, you can see through a window more easily because the outside is bright. At night, If the room is bright and the outside is dark, the window suddenly becomes a weak mirror, because light from inside the room reflects back to your eyes more clearly than the dark scene outside. These very ordinary things are all small lessons about the path of photons. Transmission through matter is not simple either. When light passes through glass, it does not simply go through like a small object slipping through empty holes. The electromagnetic field of the light interacts with bound electrons in the material. Because the material does not strongly absorb visible light photons, most of the light can continue moving through it. But that interaction changes the phase velocity and direction of travel, creating the phenomenon of refraction. A straw in a glass of water looks bent not because the straw is truly broken, but because light from the part of the straw under the water changes direction as it moves from water into air. Our eyes trace the light path backward by habit, and the image shifts. Once again, photons give us the world, but they also remind us that an image is not always the object exactly as it is. Scattering is one of the most beautiful meetings between photons and matter. If reflection is like an orderly bounce in one direction, scattering is often more like light being sent out in many directions. In the atmosphere, gas molecules much smaller than the wavelength of visible light scatter sunlight. Rayleigh scattering makes shorter wavelength light scatter more strongly than longer wavelength light. Because blue light has a shorter wavelength than red light, it is scattered more strongly in the atmosphere. When you look up at the daytime sky, you see blue light coming from many directions, not only from the disk of the sun. The blue sky is the trace of countless solar photons being redirected by molecules in the air before entering your eyes. Sunset is the gentler, deeper side of the same phenomenon. When the sun is low near the horizon, its light must pass through a longer stretch of atmosphere before reaching our eyes. Along that long path, much of the blue and violet light is scattered out of the direct line of sight. The remaining light from the direction of the sun becomes richer in red, orange, and yellow. So a red sunset is not only a symbol of the end of a day, it is a soft measurement of the photon's path through the atmosphere. Every red shade on evening clouds is a sign that light has travelled through more air, lost more of its shorter wavelength parts, and reached our eyes after being filtered through the planet. Fog, smoke, dust, and clouds create other kinds of scattering. When particles in the air are close to the wavelength of light or larger, they can scatter many colours more evenly, making the sky or landscape look milky white, grey, or hazy. That is why a foggy day does not have the clear blue of a dry, clean day. The light has not disappeared completely. It has been redirected many times, losing order, making distant images look pale and less sharp. When you look at a lamp through fog, you're not only seeing the light source. You're also seeing the photon path revealed by tiny water droplets in the air. The same is true in space. Interstellar dust can make light from distant stars appear dimmer and redder. Small dust grains absorb and scatter shorter wavelength light more strongly, leaving the remaining light looking redder. This phenomenon can be called reddening by dust, and it is different from cosmological redshift caused by the expansion of space. Without understanding the interaction between photons and dust, we could misunderstand the colour, brightness, and distance of stars. So when astronomers observe a region of sky, they do not only ask where the light came from, they also ask, what did the photon meet along the way? Was it dimmed by dust? At which wavelengths was it absorbed by gas? How was it scattered? The photon's path can always leave a small scratch on the message it carries. But the closest and perhaps most moving point is when a photon meets the human eye. Light passes through the cornea, through the pupil, through the lens, and is then focused onto the retina at the back of the eye. The retina is not a passive screen, it is delicate nerve tissue containing light-sensing cells called rods and cones. Rod cells are very sensitive in low-light conditions, helping us see at night. But they do not create detailed colour sensation the way cone cells do. Cone cells work more strongly in sufficient light, allowing us to see colour and sharp detail. Each photon that reaches the retina can be the starting point of a very small but incredibly precise biological signal chain. In rod cells, the molecule rhodopsin contains retinol, a derivative of vitamin A. When a suitable photon is absorbed, retinol changes its shape from 11 cis to all trans. This tiny change in shape activates a signal transmission chain inside the cell. As a result, the flow of ions through the cell membrane changes, the membrane voltage changes, and the amount of chemical messenger released at the synapse also changes. What is special is that photoreceptor cells in the retina do not create signals as simply as a switch turning on. They continuously adjust the signal level according to the amount of light received. From a single absorbed photon, biology has built a refined system of amplification and processing. This is one of the most beautiful moments in the entire journey. A photon may be born in the sun, travel through space, pass through the atmosphere, reflect from a flower, and then enter your eye. When it is absorbed in the retina, its physical path ends. But right there, a tiny quantum event becomes biochemistry, then a nerve signal, then an image. After that, the brain does not only register light, it compares, filters, constructs, recognizes, and attaches memory and emotion. You do not only see a flower, you may remember an old garden, a quiet afternoon, or someone who once stood beside you. A photon has no memory, but it can open the door to memory inside a human being. Color in the eye is also a conversation, not a simple measurement of each separate photon. Cone cells come in different types that are sensitive to different wavelength ranges. The brain compares signals from these cone types to create the experience of color. So yellow, for example, does not necessarily have to come from a single yellow photon. It can come from light in the yellow wavelength range, or from a combination of red and green light under certain display conditions. A screen can create many colors by adjusting the intensity of basic light components. This shows that color is a product of both the physics of light and the biology of the nervous system. Photons carry energy. The visual system turns that energy into a world with color. A camera tells a similar story, but with a semiconductor sensor instead of a retina. When a photon enters the sensor, it can transfer energy to an electron in the material. If the energy is suitable, the electron is freed from its original bound state, creating an electrical signal. The sensor records that signal at individual pixels. Many photons, falling onto many different points, create the data used to build an image. A long-exposure astronomical photograph is not something created in a single instant. It is the patient accumulation of photons. Weak photons from a distant galaxy, one by one, are gathered until a faint structure slowly appears. In a solar panel, the meeting between photons and matter has the meaning of energy. When light shines on a photovoltaic cell, a photon can transfer energy to an electron in the semiconductor material, helping create an electric current if the structure of the cell is designed to separate and guide electric charges. Here, the photon does not become an image, but electrical energy. A ray of light from the sun may travel for 8 minutes through space, then end inside a panel on a roof, helping light a room at night. That path is beautiful. Starlight is turned by human-made material into electric current, and that current can then create new light inside a lamp. In optical fiber, photons and light pulses become carriers of information. Light is guided along a very thin glass fiber because of the difference in refractive index between the core and the surrounding layer, allowing signals to travel far with low loss. Phone calls, images, data, and online messages can be encoded into light pulses moving through fiber optic cables. This means human beings have learned to use photons not only to see the world, but also to connect minds across great distances. A light pulse inside an optical fiber is not the same as ancient starlight crossing a galaxy, but it still belongs to the same family, photons carrying information from sender to receiver. In laboratories and medicine, photons in different energy ranges open ways of seeing that ordinary eyes do not have. X-rays can pass through soft tissue more easily than bone, so X-ray images allow us to see internal structures of the body. Infrared light can reveal heat. Ultraviolet light can stimulate fluorescence in certain substances. Microscopes use light to magnify the very small world. Telescopes use light to expand the very distant world. Every tool relies on the same shared truth. If we know how photons interact with matter, we can turn that interaction into understanding. But we should also remember that photons do not always let us see everything directly. A black object may absorb much visible light, so few photons reflect back to the eye. A white surface scatters many visible wavelengths, so it looks bright. A transparent object lets much light pass through, so we see the scene behind it. A glowing object creates photons on its own, or releases photons through an internal process, such as a flame, an electric lamp, a screen, or a star. A non-glowing object can still be seen if it reflects light from another source. The moon shines not because it burns like the sun, but because it reflects sunlight. What we see always depends on the light source, the object, and the photon path. Here, the path of a photon comes very close to questions about reality. The world around us has matter, shape, surfaces, and structures, but the image we experience is created when photons carry information from those structures to the eye. Without visible light, the room does not physically disappear, but it disappears from our vision. If infrared light is present and our eyes are not sensitive to it, some animals or devices may detect what we cannot see. With X-rays, the internal structure of an object may appear in a way visible light cannot reveal. This does not make the world less real. It only shows that every way of seeing is a different way of reading photons. Astronomers understand this very well. Looking at a nebula in visible light gives us one face. Looking at it in infrared gives us another, because infrared can pass through dust more easily and reveal young stars hidden inside. Looking in radio waves can reveal cold gas. Looking in X-rays can show extremely hot gas or high-energy processes. No single image is the whole truth. Each photon range tells one part of the story. When we combine different wavelength ranges, we hear a fuller symphony of matter. So when a photon meets matter, it does not only end or change direction, it helps matter reveal itself. An atom reveals its energy levels through the photons it absorbs or emits. A leaf reveals its pigments through the light it reflects and absorbs. The atmosphere reveals its molecules through the blue sky and red sunset. Cosmic dust reveals its presence by dimming and reddening starlight. The retina reveals the living power of biology by turning photons into signals. A sensor reveals the power of technology by turning photons into data. Wherever a photon goes, that place has a chance to say something about itself. And the most beautiful thing is that a photon can end its journey in your eye. It may travel no farther. It is no longer light in flight. But the moment it is absorbed, it takes part in a strange process. A small physical event becomes an image, then becomes emotion, memory, and sometimes a dream. Moonlight on a window can become a feeling of peace. Starlight in the sky can become a question about origins. Light from an old photograph can bring back a day that has passed. A photon does not carry emotion inside it. But when it meets the human nervous system, it can touch the deepest layers of experience. That is why the photon is a bridge between matter and awareness. It does not only illuminate the world like a lamp placed on a stage. It carries information from surfaces, atmospheres, stars, galaxies, leaves, faces, pages, and water, then places that information into systems capable of reading it. In a plant, a photon can become chemical energy. In a sensor, it can become an electrical signal. In the human eye, it can become an image. In scientific intelligence, it can become understanding of the universe. When we follow the path of a photon, we see that there is no hard boundary between distant light and close life. Photons from the sun make the sky blue, keep leaves alive, let human eyes see colour, help solar panels create electricity, help cameras record images, and help telescopes gather data. Photons from distant galaxies help us look into the past. Photons absorbed by matter help us know what matter is made of. Scattered photons help us see air, dust, fog, and atmosphere. Reflected photons help us see faces and landscapes. Every time light meets matter, the universe translates part of itself into a new language. And when night becomes quiet, perhaps we can think of vision in a gentler way. What we see is not the world jumping into our eyes by itself. It is the world sending photons. Every image is a meeting. Every colour is an agreement between light, matter, and mind. Every darkness is a place where too few photons reach us, or where our eyes are not sensitive to the kind of photons present. Every star is a source sending letters. Every leaf is an energy transfer station. Every pair of eyes is a place where light stops and becomes experience. A photon does not only illuminate the world, it helps the world appear inside the mind. From the moment a photon meets matter, it can become colour, heat, electric current, a nerve signal, or part of a memory. But there is still one final question, quiet and very large. After all those paths, what is the final fate of a photon? Does it truly disappear, change into something else, or keep travelling forever through the darkness of the universe? The first answer seems simple. Many photons end when they are absorbed. A photon falling onto a stone in the sunlight may increase the vibration of atoms in the stone, making it warmer. A photon entering a solar panel may help create electric current. A photon touching a light-sensitive molecule in the retina may begin the signal chain that helps the brain create an image. A photon absorbed by chlorophyll in a leaf may help move light energy into the chemical processes of life. In those cases, the original photon no longer exists as that photon, but its energy is not erased from nature. It has simply changed into another form. This is very important. When we say a photon disappears, we should not imagine it falling into absolute nothingness. In physics, absorption means the photon's energy and momentum are transferred to a material system. That system may be an atom, a molecule, an electron in a semiconductor material, a dust grain, a biological tissue, or a measuring device. The photon no longer continues along its path as free light, but its trace remains in the change it causes. A stone becomes slightly warmer, an electron is lifted to a higher energy level, an electrical signal appears in a sensor, a visual cell changes state. These are ways a photon can end without becoming meaningless. Imagine a photon from the sun falling onto a rooftop in the afternoon. If the dark roof absorbs it, the photon's energy helps heat the material. If that photon enters a solar panel, it may help separate electric charges and contribute to an electric current. If it reflects off a window, it may change direction, keep flying, and then be absorbed somewhere else. If it enters the eye of someone looking upward, it may become one tiny point in the image of the afternoon. It is the same kind of messenger of light, but its fate changes depending on its final encounter. Some photons end very quickly. A high-energy, ultraviolet photon may be absorbed by the atmosphere before it ever reaches the ground. An infrared photon emitted by the ground may be absorbed and re-emitted by a water vapor molecule or a greenhouse gas. A visible light photon may be scattered by dust in the air, move away from its old path, and then be absorbed by a more distant surface. In nature, very few paths are perfectly straight, perfectly clean, and completely free of obstacles. Light is always in conversation with its environment, and in each conversation, a photon either keeps going or gives its energy back to matter. But some photons travel for a very long time. In the space between galaxies, the density of matter is extremely low. A photon can cross enormous regions and meet almost nothing capable of absorbing it. It can leave a young galaxy, pass through immense voids, move near galaxy clusters, have its path bent slightly by gravity, and continue on. For millions of years, for billions of years, it has no feeling of the journey, no fatigue, no memory. But to us, the ones who receive it at the end of the path, that journey is a piece of history. The longer a photon travels, the older the story it carries becomes. If a photon does not meet matter, then in an ideal description, it can keep traveling. But the real universe is not an absolutely silent, unchanging emptiness. The universe contains matter, radiation, gravitational fields, dust, gas, galaxies, black holes, and on very large scales, space itself is expanding. So a free photon in the universe does not necessarily vanish because of a collision, but its wavelength can be stretched as space expands. As the wavelength becomes longer, the photon's energy becomes lower in the reference frame of cosmic observers. This is cosmological redshift, one of the deepest traces showing that the path of a photon is not separate from the history of space. A photon emitted from a distant galaxy in the visible light range may arrive to us in the infrared, not because that photon has become tired in a biological sense, not because it has used up energy like a bullet slowed down by friction. In the cosmological picture, as the space between the source and the observer expands while the photon is traveling, the wavelength of the light is stretched. Because photon energy is proportional to frequency, a longer wavelength corresponds to a lower frequency and lower energy in our measurement. The photon still travels locally at the speed of light in a vacuum, but its energy message has changed with the expansion history of the universe. This is not just a mathematical detail, it means that when we look at very distant galaxies, we are seeing light that has been stretched by the universe along the way. Familiar spectral lines from elements are shifted toward longer wavelengths. From that shift, astronomers infer information about distance, about the time when the light was emitted, and about how the universe has expanded. The photon becomes a ruler for space that is growing. It does not only tell us about where it was born, It also tells us about the path that space itself has laid beneath it. The greatest example of this is the cosmic microwave background. Those ancient photons did not begin as cold microwaves. They belong to the era when the young universe was still hot, when light and matter interacted densely. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. At that point, light could travel much more freely. The photons released from that era have traveled through most of cosmic history. For billions of years, the expansion of space stretched their wavelengths. The hot light of the beginning became a cold microwave background, almost filling every direction of the sky. A photon may begin as the brilliant light of the early universe, but after billions of years of cosmic expansion, it reaches us as a very cold, faint whisper, still carrying the physical memory of an extremely distant moment. It does not remember the way a human being remembers. It has no mind. But in its wavelength, in its temperature distribution, and in the tiny fluctuations of the microwave background, it preserves information about the early seeds of cosmic structure. From those small fluctuations, cosmologists infer how matter later gathered into stars, galaxies, galaxy clusters, and the cosmic web. Here, the fate of a photon becomes almost philosophical, while still remaining within science. A photon does not age in the way we age. We cannot sit inside the photon's rest frame because a photon has no valid rest frame. But we can say that light has a very special relationship with time. To us, a photon may travel for billions of years. In the mathematical structure of a light path through space-time, it travels along a light-like path. We need to express this carefully, but the feeling it suggests is still very deep. Light is one of nature's ways of sending an old moment to a future observer. Near a black hole, the fate of a photon becomes more dramatic. If a photon passes outside a black hole at a great enough distance, gravity may only bend its path, and then it may escape and continue its journey. If it passes closer, its path can be bent strongly, creating distorted images, rings of light, or multiple images of the same source. There are special paths near a black hole where light can orbit the black hole under very delicate conditions. But those light orbits are unstable. With only a tiny difference, the photon will either escape outward or fall inward. We need to be precise. The photon sphere, or the special light orbit region around an ideal non-rotating black hole, is not a material wall. It is not a layer of glass, and it is not a fence blocking light. It is a geometric region in space-time where light can have an unstable circular orbit if the conditions are right. In the real universe, black holes may rotate, and their surroundings may contain plasma, accretion disks, magnetic fields, and many complex effects. But the general principle is still astonishing. There are places where the geometry of strong gravity bends the path of photons into loops almost impossible to imagine with everyday intuition. If a photon crosses the event horizon of a black hole, the story changes completely for the outside universe. The event horizon is not a solid surface that the photon crashes into. It is a boundary in space-time. Once something has entered it in a future-directed path, there is no route that brings the photon back to the outside region. Not because the photon is held by an invisible string, but because every possible future path inside that boundary leads deeper into the black hole. For an outside observer, that photon can no longer send information back. It has entered a region where light can no longer become a message for us. This makes a black hole one of the deepest endings for a photon's journey. A photon may cross billions of light years, avoid dust, avoid gas, pass through empty space, and then, if its path leads across an event horizon, it no longer belongs to the observable sky. But a black hole is not only a place where light is lost. Matter outside a black hole, inside the accretion disk, can become violently hot and emit high-energy photons. The gravity of the black hole can bend light, creating the black hole shadow and glowing rings distorted by gravitational lensing. So even in a place where light cannot escape from within, photons outside still help us recognize the shape of the darkness. Some photons do not fall into a black hole, but the black hole changes their fate. A photon from an accretion disk may loop partway around the black hole before escaping, causing the image of the glowing region to appear distorted. A photon from a star behind the black hole may be bent, making the star appear shifted from its true position. A photon leaving a region of strong gravity may undergo gravitational redshift. In all of these cases, the black hole does not necessarily swallow the photon. but it rewrites the photon's path. And precisely because of those rewritten paths, astronomers can infer the existence and properties of dark objects. A photon's fate may also be to be recorded. When a photon enters the sensor of a telescope, it may create a signal electron. That signal is amplified, stored, processed, and then becomes a point in an image or part of a spectrum. The original photon disappears in the sensor, but its information is preserved as data. A distant galaxy does not step into a computer, only its photons arrive. But when many photons are recorded, they create maps, graphs, images, models, and eventually understanding. This is a very special fate. The photon ends by becoming information that can be shared among human beings. A photon entering a camera is similar. It no longer keeps flying after being absorbed in the sensor, but the absorption event is converted into electric charge, then into a numerical value, and then into an image. A photon from a face can become a point of light in an old photograph. Many years later, that photograph may emit new photons from a screen, or reflect photons from printed paper, sending them into the eyes of a viewer, and memory comes alive again. In that chain, the old photon has disappeared, new photons have appeared, but image information is carried across many forms of matter and light. The universe does not preserve every photon intact, but it can preserve patterns of information through transformations. A photon's fate can also be to scatter many times. In a cloud, sunlight entering the cloud may be scattered again and again by water droplets and ice crystals. Each time the light changes direction, the photon may be described as light continuing in a new direction, or in a deeper interaction picture, electromagnetic energy may be absorbed and re-emitted by matter. The result is that clouds look white or grey, light becomes diffuse, and shadows soften. When you stand under a cloudy sky, sunlight no longer comes from one brilliant point alone, but from the whole dome of the sky. The photon has lost its original alignment, but in return, it creates a gentler light. In the distant universe, scattering once played a fateful role as well. Before the universe became transparent, photons constantly interacted with free electrons. They could not travel far along long straight paths. The universe at that time was opaque to light. Only when electrons combined with nuclei to form neutral atoms could photons move freely across large distances. So the cosmic microwave background marks a major change in the fate of photons, from being trapped in a plasma fog to being released into expanding space. Once released, those photons continue travelling until they are absorbed by a device, a dust grain or some other object. In the very distant future, the photons left in the universe will continue to have their wavelengths stretched if the universe keeps expanding. The cosmic microwave background will become colder and colder, its wavelengths longer and longer, and it will become harder to detect for observers in the extremely far future, if any exist. Light from galaxies outside the nearby gravitationally bound group may eventually never reach us, because accelerated expansion makes cosmic horizons important. This does not mean photons disappear instantly, but it shows that the fate of photons is tied to the fate of the universe itself. In a growing universe, light does not only travel through space, it is stretched by the history of space. We might ask, if a photon travels forever without meeting anything, does it still have meaning? Physically, it is still electromagnetic radiation, and still has energy in an appropriate observational frame, even though that energy may become lower and lower because of cosmological redshift. But as information, its meaning only opens when some system absorbs or measures it. A letter that is never opened still has content in the sense that it carries structure, but that content has not yet become understanding. A photon that has never been absorbed may still carry physical information about its source and journey, but that information only becomes knowledge when an eye, a sensor, a telescope, or some material system receives it. This is the beautiful point of observational science. Measurement is part of the photon's fate. When a photon is measured, the whole secret of the universe does not appear all at once, but one very small fragment is recorded. One photon gives us one grain of data. Many photons give us an image. Many images give us a law. Many laws give us a model of the universe. From separate quanta of light, human beings build an understanding of stars, galaxies, black holes, the expansion of the universe, and the ancient light left from the beginning. The photon ends inside the measuring device, but its story continues in intelligence. If we look very closely, the fate of a photon may be a microscopic transformation. It changes the state of an electron. It makes a molecule vibrate more strongly. creates charge in a sensor, it activates retinal in the retina. If we look very far, the fate of a photon may be a cosmic message. It may be stretched by space, bent by gravity, swallowed by an event horizon, or preserved in astronomical data. It is the same quantum object, but when placed in different contexts it can become warmth on skin, the green of a leaf, the darkness of a black hole, or evidence of the moment when the universe became transparent. And no matter how it ends, a photon always serves one message. The universe tells stories through light. If a photon is absorbed by a stone, it tells a story as heat. If it enters a human eye, it tells a story as an image. If it enters a solar panel, it tells a story as electric current. If it comes from a distant galaxy, it tells a story through redshift. If it is bent by a black hole, it tells a story through the geometry of space-time. If it belongs to the cosmic microwave background, it tells a story as the cold echo of the cosmic dawn. A photon has no spoken words, but it has many ways of becoming evidence. Perhaps that is why the question, does a photon disappear, needs to be answered gently. Yes, a specific photon can end when it's absorbed. Yes, it can change form into heat, electricity, chemistry, or a biological signal. Yes, it can be carried by a black hole into a region that can no longer send information outward. Yes, it can continue through empty space for an unimaginably long time. And yes, in an expanding universe, its wavelength can be stretched until the energy we measure becomes extremely small. But sometimes, the most beautiful fate of a photon is not to keep flying forever. Sometimes, its most beautiful fate is to stop exactly where it can be understood. An ancient photon from the cosmic microwave background can travel through almost the entire history of the universe, then be absorbed inside a sensitive antenna. In that moment, its free journey ends. But it contributes 1 point to the microwave map of the sky. That map helps human beings measure the background temperature of the universe, find tiny fluctuations, and understand the seeds of large-scale structure. A photon from a distant galaxy may die in the sensor of a telescope, but it helps us know that the galaxy once existed when the universe was younger. A photon from a star may end inside your eye, but it helps you feel the night sky. When a photon is seen, measured, and understood, it becomes knowledge. And here, near the end of the body of this journey, we can hold on to a very quiet image. Out there, countless photons are still travelling. Some have just left the surface of a young star. Some were born in a disk of hot gas near a black hole. Some are light reflected from a distant planet. Some have travelled since the universe was very young, and now remain only as a cold microwave whisper. Some will be absorbed by dust, some will enter a telescope, some will never meet a human eye. But all of them are tiny streams of natural information, carrying traces of where they were born, the path they travelled, and the final encounter awaiting them. So the fate of a photon is not simply to disappear or to exist. Its fate is transformation, from light into heat, from light into electricity, from light into chemistry, from light into a nerve signal, from light into data, from data into understanding. That path connects physics with life, black holes with telescopes, the cosmic microwave background with a question inside the human mind. A tiny photon may never know what it is doing. But by travelling, by meeting, and by being absorbed, it helps the universe tell its own story. And so we have followed the very long path of a photon, from the smallest nature of a light to the greatest distances of the universe. We have seen that a photon is not a simple bright particle flying through darkness, but a quantum of the electromagnetic field, a messenger carrying energy, wavelength, direction, and information. It can be born inside an atom, in a flame, in lightning, in an aurora, in the core of a star, or from the time when the universe was still very young. It can travel through space for a few seconds, a few minutes, a few years, or billions of years, until one day it touches a human eye, falls into a telescope, or becomes a signal inside a measuring device. From that journey, we understand that seeing light means seeing into the past. The moon we see is the moon from a little more than 1 second ago. The sun we see is the sun from more than 8 minutes ago. Distant stars and galaxies are letters of light that began their journey from older ages of the universe. We also understand that when a photon meets matter, it does not only illuminate things, it creates colour, warmth, electric current, photosynthesis, images in the eye, and even the data that help human beings read the history of the stars. A tiny photon can tell us how hot a star is, how fast a galaxy is moving away, how cosmic dust has absorbed light, how a leaf has received energy from the sun, and how the ancient radiation of the universe has been stretched into cold microwaves across billions of years. It is not only light, it is the correspondence of matter, the trace of space-time, the way the universe sends the past into the present. And now, as the story grows softer, let this thought remain gently with you. Out there, in the vast darkness, countless photons are still travelling. Some have just left young stars, some have travelled longer than all of human history. Some will be absorbed in dust, in stone, in water, in a leaf, in a pair of eyes, or in the mirror of a quiet observatory. And you, tonight, no longer need to chase the light. Just let your breathing slow, relax your body, and rest in the quiet of distant things. Sleep well. I will see you again on the next journey with Drift into Quiet Knowing, where we continue listening to the universe tell its stories through the smallest things.